Hello and welcome everyone to another session in the Data R series. We are thrilled to be here you this evening for a session full of action-packed learning. I am Sambhav Jain, part of the data science team at Analytics Vidhya. For those who have joined us for the very first time, a brief introduction of the data hours sessions is the data hours is a series of webinars conducted by Analytics Vidhya and led up by top industry experts. It is a fun way to understand the concepts of data science from the leading players in the data tech domain. And as the name suggests, it is 1 hour dedicated to data. So we are hopeful that these sessions are going to be great source of enrichment and value adding for our community members. So now on to our session today, which is our today's session on extracting values from data. So in that data R, we covers in this data R we cover topics like types of data, structured, unstructured data, basic data, checks, variable types, skewness, variance, null value, etc., outlier detection and its treatment, data transforming, and redundant variables, reducing data complexity, data sets examples across different industries and their use cases, data wrangling concepts, etc. So I have you all are excited to attend this data hour with us. So before we kick off things off, and I hand it you to the today's our speaker. So quick recap of housekeeping items like we are recording these sessions and we will make the recording available in a few days on our YouTube channels. So please also you all can use the Q&A session for asking any questions you might have during the sessions as well, and we will do our best to answer them as the data progresses or towards the end. So also we will share a poll about the feedback of the session towards the end of the session, so which I requested you all to kindly fill up. So now on to our speaker in this session of data R, we have Varun Behel with us. Varun is currently working as data science engineer with Adobe in Bangalore. He has more than 5 years of experience in data science profession and has worked with various kinds of data covering industries like telco, e-commerce, pharma, retail, Musilgma, and web analytics. So he also has keen interest in research side of like machine learning with NLP, forecasting, segmentation, and recommendations being areas where he contributed significantly for enhancing the existing scope of traditional modeling techniques. So that's uh, about our today's speaker, uh, Varun Behel. So over to you, Varun. The virtual stage is all yours.
Thanks, Saurabh. Hi, everyone, and thank you for taking time out for this session. As the title says, we are going to talk about the data primarily, and as the topic says, it's called extracting value from data. So, primarily covering all the aspects of data from understanding what all variables it has, how to understand what kind of variable it is, what are the properties of the variable, how do we understand um, how to deal with different kind of data sets. It also caters to the problems of outlier detection and treatment, which is primarily the most important aspects when we are building any machine learning model. Data transformation and processing is also a key aspect where we want to understand what's the dimensionality of the data and what transformation will help us in structuring it in a way that is suitable for a best fit model. Then briefly, we'll talk about data wrangling operations that you can in day-to-day life if you want to become pursue data science field. That is one basic step that you would need, and in any particular language that you code in SQL or Python or R, these are the basic aspects that we are going to cover. And lastly, we're going to talk about some data sets example And along with that, if there are any question and answers, I'll be happy to answer those as well. Being said that, let's begin with the session. And the first topic of this session is types of data. If we if we look at the various types of data, we can further classify them into unstructured and structured format. Primarily, the structured format is which is already in a format in which you don't need to do much of a cleaning. It is already in a form which is a reusable form, or you can directly use that to build a model. Whereas unstructured data is anything that you can be scraping from different websites. It could be scraped through an API, or you are maybe translating a particular Word document or a PDF document into something. So every data, when we talk about the source of the data, I've given 4 classification to understand how an unstructured data and structured data are different. So unstructured data is an unorganized form. It's obviously a qualitative data. We do not have categorized into a quantitative form. So the capturing process of the data can happen through the web session log. Whenever we are traversing any website, the cookies track what our behavior is on the website, clickstream data on the website, transaction data. All this, when it gets captured in the raw form, it's primarily very unstructured, and there is hardly what we can do to create any value out of it. So it requires a lot of pre-processing, a lot of sophisticated techniques are on top of that applied to properly create into a structured data form. Now, in terms of the storage, the two types of the data, one can be actually stored in a relation database where you are having a SQL database. It could be an Redshift environment, or it could be a Hadoop environment where these relation databases are stored. There are well-defined columns, and they're attributed, whether they are integer column or a numerical column or a categorical column. Whereas when we talk about unstructured data, no such classification is available. That's why they're kind of stored in data lakes. In current world, we primarily use large amount of unstructured data, and we are stored in S3 buckets or a large pool of servers that are there in-house to any company. In terms of operationability of these two kind of data, unstructured data is non-scalable. By non-scalable, I mean if you want to process it the way you process the structured data, that means if you want to query this particular data, or you want to apply some data wrangling operation, that will be a fairly difficult task. The search operation, if you want to search any particular thing, all these particular aspects are very difficult to address when we are talking about this. Now, what differentiate between, like when I'm saying structured data is scalable, what makes it scalable is the way it is structured in a relation database. These are usually partitioned or distributed in a way that there is a particular primary key that will help you in differentiating what is the level of the data. So if a data is leveled at a set of columns, then you can fairly classify it into a structured data, whereas unstructured data will not have any primary key or anything that helps us in identifying what could be the level of this data. That is where the transformation is done on unstructured data to make it in a format that is usable. Now, unstructured data requires a lot of sophisticated methods like NLP, natural language processing, to actually make sense out of the textual fields or the image or anything that has been directly in the raw format been scraped out. And it requires a lot of cleaning to particularly create some columns out of it, some variables out of it that will actually make sense. So that is a gist of how we classify our two different types of data. Whereas when we finally transformed ourselves into a structured data format, there are certain categories of column that would exist in so in a real industry, if you look at any kind of data set, there'll be different kind of variables that would be available. I would further classify these variables into a nominal data, an ordinal data, text fields, discrete, which could be a category, continuous data, and date timestamp. So in any real-time data, you will always find these 6 components available in some or the other format. When I'm talking about nominal data, it caters to anything that is related to gender, ethnicity, area, hair color, locations, and all those. So kind of, it is also a categorical field, but it has a factual reference to it available. Whereas when I'm to differentiate it between the discrete or category fields, it is the field that is created by someone. It's a derived particular categorical variable. So we could even consider our customer names, customer ID or session IDs as a part of a discrete factor variable. Even our channel names and product names are also part of it. Because in the raw format, you don't need usually find these attributes, whereas we transform them and derive them into a format that is usable. Continuous data is all numerical fields or float variables that we usually deal in our day-to-day life. It could deal from salary, revenue, number of order purchases that can be happening on a website. So every continuous field that is integer or could be have decimal points if it's related to salary, revenue, or any cost related attributes. Even ratios that we usually see in our day-to-day daily life that also come under the category of continuous data. We would always see if we are dealing with the time series data that there are date and timestamps. Even for non-time series data, there are usually date annotations that are given to understand on which day that particular row was edited in the data or it was appended in the data. So these kind of timestamp field helps us in understanding how the data is being captured, what was the chronological order in which the data has been captured, and it helps us in sorting and all the further exercises that we do on the data. There could be a lot of text fields when we primarily talk about data that caters to or is built based on surveys or the website that is scraped. This data is in a very raw format, could be customer feedback and reviews. So these kind of fields actually increase the size of the data, but they are clearly important as the information in them is in a very raw format, and there can be a lot of use cases that can be developed when we clean these particular fields or create a structure output from these particular fields. Now, ordinal data is it could be categorical or it could be integer, but it is something that you can sort it. So if we are, let's say, given age of a particular patient in a particular data, that can be sorted based on any even ascending or descending order. So these are the kind of data aspects that you can sort. It could be even in the categorical manner that you have said, but there is a property to which based on which you can sort them. Moving further, wanted to touch base on what are the necessary data checks and the cleaning step that you should do. So this is where your exploratory data analysis starts. So let's say you have a huge chunk of data and you want to understand what is the approach that I want to follow in understanding or deducing the right characteristics of the data. So when we talk about necessary data checks, we should easily first classify them into a univariate test and a multivariate test. On this screen, you will currently see a univariate analysis. What I have done here is in which you first check what are the data types of the different columns that are available. So in a particular data scenario, you will have a lot of columns in your data, and you would like to understand what data type it has, because understanding the data type tells you what is the next step that I want to do in understanding the statistics of this particular field. So if there is a numerical data, you will come across variables like that could be data having data type of int64, float, num64, or similar integer. In categorical, we might come across class, object, or factors. All these tie back to only categorical fields. Numerical fields could have properties like int, float, or numerical 64. Now, these are the types that you will obviously see when you are maybe coding in Python or understanding whether to seeing the summary of that particular field, whether it falls into integer category or a float category. Even in SQL, the similar approach can be dealt with, and you can understand what the data type is. Now, let's say we understand the data type is numerical or it's a continuous data. So you can go through the various statistics, and that is the first step I would recommend everyone should look into. These are the basic stats that you must be familiar from mathematics. Checking the mean of the particular column, checking the min and max of the particular column, checking the median of that particular column, and similarly standard deviation and percentile values. There are other two important aspects to other than the standard statistics, which is kurtosis and skewness. It helps us in understanding what kind of bias the data has, or whether it has a high variance or it is normally distributed. Similarly, when we talk about categorical data, we talk about distinct counts that are there of the number of categories that are there, how many missing values that could be there, and the frequency count across categories. So let's say if there is a category of a hair color of the citizen in a particular area, there could be a lot of people with brown hair, there could be a lot of people with black hair. got a people with who have colored their hairs in different colors. So that frequency distribution tells you that which category is prominent and then which category is least prominent. And the visual checks that usually will help you in understanding these particular univariate tests primarily is box plots and histogram. There are very sophisticated visualization approaches available, but the standard, if you are starting with any analysis, box plot and histogram gives you enough information in understanding a continuous field, and that will also tell you what kind of bias exists in a data, whether it is rightly skewed or right inclined towards the values or left inclined towards the values. Now, what are the cleaning ways that we could initially talk about when we have just seen the data? These are the first steps that everyone should be taking care of and in their data set. So always check for the duplicate values in a particular row. So when you get an overall data, you should always dedupe that particular data in understanding what is the right level of the data. If there'll be duplicate records, you will never be able to identify the right level of the data. And identifying the right level of the data is a key approach that you do even in your further exercises of wrangling. Even if you are merging with another data set, you need to have the right level in place. Then only you can merge with any other data set. Talking about the null values kind of exist in all of the real life data examples that I have come across. And sometimes null values make sense and sometimes they don't. So there is always a business sense to be applied when you're looking at what should be the right approach to deal with the null values. So if the null values in a particular column is not making sense, it should be imputed either with a mean value or a median value. We'll be further talking about this particular problem statement, then how to cater to the null values. Now, date field that are existing in the data sometimes get classified in the numerical format, sometimes in a categorical format, or sometimes as text. So we should always make sure that we convert them into the right timestamp and date field, because that is important whenever we are doing any sorting exercise. Talking about a textual or a categorical data, we've always seen there are some kind of typos that might exist in the data, and there is a need to deal with those typos. So there are a lot of sophisticated approaches as Euclidean distance and fuzzy matching available that you can apply. But even before that, you should check for any white space, any unwanted text, any special character like @ hash, underscore, slashes. You should be not having this in your data when you are cleaning them. There could be fields in which you could have some suffix or prefix added to the data, and you might see that as an redundant information, and that is also an information that you can obviously remove from your data set. So this is a kind of approach that I would recommend everyone to follow when they are starting with any data check exercise, and then what was the first cleaning step they had to apply. Now, in terms of multivariate data checks and cleaning exercise, here I'm going to cover what are the multivariate ways of checking whether a particular variable in the data is a right fit, whether we should be keeping it in our data set. Does it make sense to keep that in when you are running a machine learning model? How do you come to a conclusion that this particular variable is important for us or not? Now, there are different kind of statistical tests that are available, and you can obviously apply in understanding this. You can obviously plot between two variables, a scatter plot, to understand what is the relation between them. There can be a correlation test done between variables to understand whether a particular variable should be kept or the other variable should be kept. Now, in terms of the tests that you can apply to, and that will also help you in cleaning out unnecessary variables out of your data. One is the t-statistic test. Now, this t-test is not a normal t-test, it's the t-test of independence. When I'm saying independence, it basically checks whether two variables are associated with or not. And when we talk about association, we usually talk about association in terms of means of the variable or a median of a variable. So if I'm comparing an age column to a revenue column, and I want to understand whether they are very associated to each other, then I will take a call whether to keep a revenue field as a continuous variable in it, or age field, whichever is making more sense to me in terms of the use case of the problem. Now, if the T statistic says that the both, like we are basically testing our null hypothesis here. Whenever I'm talking about a statistical test here, it is about disproving or approving your null hypothesis. So if a null hypothesis is not disapproved or it holds true, that means both the fields are similar to each other and you might have to drop one of them, or you could do some feature engineering to combine them to create one out of them. Now, if I'm talking about T statistic, that is primarily used for comparing two variables, and those should be continuous. By continuous, I'm saying it should be in a numerical format. You can do standardization or normalization, but even if you are checking in the raw format, it will give you a basic interpretation of whether which particular variable to keep. Now, every statistical test gives you an output in a p-value format. If someone is not familiar with p-value is the point in a normal distribution which helps you understand whether it falls in a critical region or not. Now, if a p-value of a particular test comes out to be less than 0.05, then we can fairly say both the variables we can keep, and they are significantly different from each other. Similarly, when I'm talking about categorical tests, I'm talking about categorical variables, I need a different test other than the t-test. Chi-square test of independence is primarily applied in understanding whether two variables are associated to each other in any way. Again, chi-square also will generate a p-value for you. There is a chi-score also associated to it. So you can take a call as per whether you want to understand as per p-value or chi-square value, whether both the categorical fields make sense in the data, or whether we need to keep one and eliminate the other one. I've also added a table here of level of measurement, which basically tells you what kind of variable, if it's a nominal variable, and if you want to compare it with another sample and what kind of sample it is, what kind of test you can apply. So these are the kind of tests that you can always have access to, and you can obviously apply in any of the tools that you are familiar with. You can do these exercises even on an Excel, even Python always has modules available for these particular things. And you can even create the formulas for these and can apply the same statistic and get an output on a SQL platform as well. Now, moving forward, what are the ways in which you would be able to interpret these test statistics? We talked about the p-value, but there are other two key aspects in which helps us in understanding whether our data is fit for building a model or not. Now, here I want to focus on a bias and variance trade-off, and you will always keep on hearing these terms when you are starting your data science journey, or even when you are solving real-life data science problem. Bias and variance are the two killers which can hamper your model accuracy. It can cause misfit of your model. So how do you first get an intuition that your model might be skewed or might be biased in a particular direction? So skewness and kurtosis are two kind of tests that people primarily use in understanding whether there is a high variance in the data or high bias. There can be other approaches in solving whether your mean is closer to the 99th percentile value of that particular field, or mean is closer to the first or 25th percentile value. Both these ways are easy to identify whether the data is skewed on one direction or not. Here I've shown two examples. When the skewness is less than 1, the data seems to be rightly skewed. So that is an indicator that there is some bias existing in the data, and we might have to cap or do some cleaning of those lower values or those outlier values to create a normal distribution. Because normal distribution is kind of a right format that you would need to build any traditional machine learning model. And that is one of the basic assumptions of our linear and logistic regression tool. Talking about skewness, if it is higher than 1, then we might say that the data is left skewed. And then again, it requires a similar way of treatment. And this skewness basically is an indicator that there is some kind of bias available in the data. Now, if I want to understand what is variance in my data, I could basically plot a scatter plot and understand if it is not falling and the values are scattered across the entire X and Y axis, then probably there is a very heteroscedastic data which is basically a term given to a high variance, or the data that when checked with a dependent variable shows you an unfit plot. Now, kurtosis is a measure if it is closer to zero, it is basically tells you the data is centrally aligned or it is symmetric. And when the kurtosis value falls away from zero, it is basically due to some kind of variance that is available in the data. And that is not good when you're fitting any model. Now, what are the possible challenges that you might face, or what the possible outcomes that might see when you are seeing high bias or high variance in the data? Whenever there is a high variance, your model will tend to overfit, because these are the noise points that a model picks up and tends to understand this as the right value. And whenever you are doing any sort of prediction, say regression or classification, you will always see your model overfitting when you are testing it. Whenever there's a high bias in the data, the model tends to underfit. There is a bias towards some set of values, and when you in the test data you will not see those kind of values, the model will underfit and it will be never be able to predict those values correctly. So the optimal good balance is when we have a data set in which, or a variable which is treated for low bias and low variance. So there are a lot of approaches that we're going to further talk about in the upcoming slide on how to treat this low bias and low variance. And primarily what we are going to talk here about is the outlier treatment of every of these variables, which kind of helps us in reducing the bias and variance in the data as well. Now, outlier detection and treatment is basically a treatment step that outlier could exist in the data, that could be based on the capturing issue. This could be a data outage, could be a data spike, could be redundancy in the data, or could very well be a human error as well. All these possible scenarios can lead to an outlier in your data. But there is a utmost need to understand what these outliers are. There has to be a proper way in understanding how to identify and whether or not we should be eliminating these outliers. Whenever we are talking about outlier detection, it is a kind of a sensitive approach we should be following to it, because there are certain outliers that might make sense as per the business logic. So if this caters to a business value, if that particular lower or a higher value that we see in a data, if it still has some justification as per the business, there has to be an intent to keep it. But there has to be some kind of treatment to be applied to that particular outlier as well, so that it makes sense in the overall sense of that particular variable. So there are various ways of checking an outlier, but I would be fairly talking and concising them over the two approaches, which are fairly easy to understand and easy to implement as well. So first one is the box plot or the interquartile range. Whenever we distribute our data set in a box plot approach, it qualifies the data in a confidence interval range. The confidence interval range is basically your what is the first quartile range to the third quartile range. In simpler terms, what is the 25th percentile value to the 75th percentile value. As per what you get in your data, you can obviously extend your percentile value. Some might like to use the 5th percentile and the 95th percentile. Whenever we are talking about a t-test or anything, we usually consider 5th percentile value and the 95th percentile value as the range of our confidence interval. Whereas when we are talking about IQR, we usually keep it the capping at Q1, Q3, which is nothing but 25th and 75. Again, when I'm talking about Z-score, it's also another way of checking your outliers. Here we are checking whether it falls in a critical zone or not. If you look at the below chart, I'm showing a normal distribution plot. And there is a critical region that basically hints that if a value falls in this region, it is primarily an outlier, and there should be a particular approach to cap it to a certain level. So Z-score greater than 3 or a p-value, whenever you are running a Z-test, if it is less than 0.05, it falls in the critical zone. And that is an indicator that you should be not keeping those values when you are building a model. So capping and flooring can be applied to both interquartile range and Z-score. The idea is that you keep the values, higher values. If the value is greater than Q3 values, you cap them at that particular 75 percentile range. And if it is a lower bound value, let's say if it is a very low value, it's lower than the 25th percentile value, and you feel that does not make sense in the whole sense of the variable, then you should be doing something known as flooring, and you should cap it at the Q1 value, which is nothing but the 25th percentile. Similarly, for capping with respect to the Z scores, you should be considering the values you see at Z equal to 3 or Z equal to -3, because that is the range that still falls in your confidence interval, and that is fairly easy to understand that why it was capped under this range. The other two commonly used approach, and that might or might not fit in every use case, is mean and median imputation. And when we are talking about categorical fields, it's usually replacing the null values or the outlier values with the most highly frequent or the most low frequent category available in the data. Now, when I'm talking about mean and median imputation, you can obviously use this particular approach for treating the null values, whereas for the outliers, it might or might not make sense every time, because sometimes an outlier is also related to other variables that are existing in the data. It might be interdependent or correlated to any other field. So before imputing based on mean or median, you should always check whether the value makes sense with respect to other variables or not. So that is one basic check that you should always keep in mind while doing these imputation exercises. I also wanted to share some real world examples that I have also came across, and how I have treated these outlier. Here I'm taking an example of a Google search trend for a specific keyword, and I've extrapolated it across weeks. Here we can see there is a clear dip in the data, and then again, after the dip, there is a sudden spike in the data. Now, these two could be an outlier, but based on my visual sense, I know the trend cannot deviate so much, so it can be classified as an outlier. So when I do a normal distribution or plot a histogram of this, I can clearly see there are certain low values that are falling in the critical zone and are not letting the distribution to look normal. Whereas if you consider the distribution from here onwards, it fairly looks like a normal distribution. Whereas these values should be treated in a way that it falls in a critical zone. I also went with an approach of box plot, as we were discussing. It is basically checking whether how many values falls out of your interquartile range. So there are certain high values and certain low values, which I can clearly see are out of my confidence interval zone, and I should take a call in capping or flooring them to make sense. As I was previously mentioning, outliers should also be looked from a business logic. And here in this particular scenario, this dip could be cause of a particular holiday that had a huge impact on the trend of that particular search keyword. Whereas it could also be an event that could cause and data outage that could be causing. So there has to be always an explanation to be provided whenever you are capping or treating your outliers, because it's important to understand why that particular thing has occurred in the data. Moving forward, I would like to now touch base upon the next aspect of um, data understanding, or you can say this is the first step of feature engineering. So feature engineering in data science means that you are transforming your variable into a format that is best utilized or best fit when you are building a particular traditional model. When you are saying data transformation, when you're talking about data transformation and scaling approaches, they help us in reducing the variability and the complexity of the data as well. I will be taking questions at the last of the session, so for anyone who's raising hand. Now, talking about data transformation and benefits, variables that possess high bias and high variance, and even after doing some kind of outlier treatment, you still feel there are certain values that are leading to skewness in your data, and you need to amend those particular aspects in your data, because a highly skewed data might not lead to a right outcome of the model as well. So there has to be a sophisticated approach that you or a robust approach that you apply in transforming on scaling your data. Most of the ML algorithms, whenever you are building your training data sets, need these kind of approaches to be applied prior to them. These are the algorithms that helps us in compressing our data in a particular range, particularly talking about the continuous field, because that is the range in which the model will behave the best. Else, if the variance of the value, or if taking a random example of a revenue field, the value might range from 10 rupee to 10 lakhs. So there is a high variability in the data, and the model tends to deviate from the actual behavior whenever this kind of variability exists. So how to curb these or cater to these caveats that exist because of skewness or because of any variance that exists in the data? We tend to resort to something that is called as scaling or transformation. Now, there are a lot of techniques that are available, but we need to understand when to apply and where to apply which kind of technique. There are scaling techniques like min-max scalar, which is also known as standardization. There is max absolute scalar, which is in which we scale our values between -1 to 1. All these approaches are kind of used to normalize our distribution. So the approach that we follow in any of these transformation technique is to create a normalized output of our data. I will also be showing few examples of I will also be showing some examples where I have taken some real world data example and have treated those. And how do we see the transition from their skewness to a normal distribution? So if I briefly talk about these transformation techniques, it caters to a min-max scalar, which is scaling values between 0 to 1. It's again compressing those. A quantile transformator, which is the most best fit transformator that is available out there. So that also kind of treats your outlier and compresses the value between the quartile range. Log transformation is kind of or exponential transformation is some applied whenever you see a lot of skewness in the data, and you cannot treat it with the basic techniques that we were previously discussing. A normalizer is something that changes your mean to a zero value, and your entire sum of your range would look correspond to a sum of absolute value 1. So these are some kind of transformation, and how to visualize them and how they actually look in a data set. I've given some example here. Now, there was a happiness index data that is openly available on Kaggle, and I took the data set example from there. Now, if you look at there was in this data, there was a score fields available for generosity. Now, the generosity field seems to be kind of skewed on the left side. And when I apply a min-max scalar or a standardized approach, it kind of translates itself into a normal distribution. Now, this kind of approach is important because now I have solved the problem of skewness in this, and it is usable for me. In this log format, there is a perception of corruption score available, and clearly this is left skews. After applying log transfer, although it is still not ideally normally distributed, but is fairly in a format that you can use and help in building your model. And taking example of robust scalar, it reduces the impact or compresses the values that are high and can be reduced to the values. So these kind of values are helping, or you can say are deviating us from a normal deviation. So robust scalar kind of suppresses those deviation values and gives you an output that is fairly looking like a normal distribution. So these are kind of techniques that you should always keep on whenever you're building a regression or using any classification techniques, because these models do have these assumptions in place that if there is a standardization technique applied, you will be getting a better outcome to whatever use case that you are solving. I will take a pause and look at some question and answers that people have asked here. So age can be both continuous data and nominal data. It depends if it is binned in a categorical form, let's say 10 to 20, 20 to 50, and so on, it will fall under the category of nominal data. But if it is given in a continuous format of an integer, we can consider it as an continuous data. So Kramer's V and chi-square test of independence. Kramer's V basically tells you an association. It is basically a correlation approach that you apply for categorical variance, whereas chi-square test basically tells you whether both these things mean same or not. Two trend lines can be following the same trend, or two categories might be telling you the same thing, but their values might be talking differently. Chi-square test also tells you that kind of association, that whether their means end up in telling the same story or not. So whenever there could be a correlated field, But to identify, there could be two categories that might not be correlated to each other, but could be still associated with each other in some other way. That is why we take another approach of chi-square on top of Kramer's V that you can apply. Talking about capping and flooring technique in a bit detail, whenever there is a high value or a spike in the data that doesn't resonate with the entire data fields, you should be applying capping. You should be applying something called capping. It is basically masking those high values to a lower value, and those lower value can be your choice. It could be a 75th percentile value, it could be a 95th percentile value, but it should resonate with the entire flow of the data. So whenever I'm talking about a normal trend, let's say an order purchase every week, continuously we were seeing that the order were between a range of 80 to 100, but suddenly in a certain day the orders were placed in excess of 1,000. So it could be a data tagging issue, it could be a capturing issue. So in those kind of cases we have to cap. And the two techniques that I was talking about are either you cap based on the z score, which is z -3 or z3, which is just at the point or the verge of the critical range. And if you want to understand based on the interquartile range, q1 or q3, in short, 25th percentile value of the continuous field or the 75th percentile. So last question, I will be talking on the topic that we were previously covering, which was transformation. The how data transformation helps us in understanding or helps the model in understanding. So you need to understand that if there are large value, the model will always behave or will be attributing a particular outcome based on the large values in the data. So if they are scaled, they are compressed in a particular range, no value is discriminated from each other. You don't want a field that is of a revenue and that is again compared against age or number of orders or similar low value continuous variable fields to be deviated and the entire focus coming to the revenue field because of the high volume that exists in the data. So to avoid those kind of situations, we transform data, scale them, it means 0 to 1, -1 to 1. That also enables us in fitting the basic assumption of most of the model that there should be a normal distribution in your particular numerical field. That helps us in further building the right model for it. Now, even in categorical data, there has to be some sort of feature engineering to be applied. The two kind of basic steps that I would say are most commonly used are label encoding and one-hot encoding. What you can do is if you have a categorical field, let's say salary, high, medium, low is categorized, you can encode them into 1, 2, 3. Now for the model, it will understand that 1 is for high, medium is too low. You can even rotate the encoding as per your choice. You can put 3 as high, medium as 2, and 1 as low. So that is encoding is as per your choice, but the aim is to create it into a continuous format. The other way, and which I feel is a better way of dealing with categorical fields, is creating binary fields out of this. So for a high categorical row, you will only have a binary flag 1 when you are corresponding or talking about that. Similarly, for a salary medium low, there will be a medium associated in there, and for a salary low, on the lower row field, it only will be flagged as 1. These two approaches will fairly help you in dealing with how to put a categorical field in the data, because most of the modeling techniques, if you talk about SVM, logistical linear regression, or any naive-based kind of approach, you need to create them into a format that the model understands. And the binary fields are the best kind of fields that you can generate that the model is easily will be able to understand. And it is for you as an analyst is interpretable as well. You can easily explain because of such value, this kind of thing is happening. Now, feature engineering, as we talked about transformation techniques, we talked about capping, flooring, we talked about how we can treat our outliers. They can both lead to increasing the dimensionality of your data and even reducing the dimensionality. The end goal for us is reducing the dimensionality of the data. So as long as the dimensionality of the data is controlled, you will be able to train your model faster and even generate the output faster. Higher dimensional data takes a lot of time in training, and even the output could be even scattered. It could be deviated from the outcome that you are expecting to be. So how can dimensionality of the data increase? If you are, let's say, I was just taking an example of 181 coding. If let's say there was a categorical field of 25 categories and you do a one hot encoding and you basically create binary fields, 25 binary fields for that. So that basically adding 25 new variables to the data. Similarly, continuous variables, when you derive them or you convert them into a new format, that also adds a new format. When I'm talking about continuous variable, you can be creating a lead lag variable out of it. You could be creating bins out of those variables. You could be bucketing them into particular thing and creating a new form of variable. All these things add to increase in the dimensionality. When we are dealing with textual data, we tend to create n-grams of those particular fields, and that also adds an additional column. Basically, they will cater to every word in that sentence of a field is capturing into a column, is getting created into a column. Now that could be a binary column, but overall the dimensionality of the data is increasing. Now, what are the ways in which you can, as a basic data science analyst, how can you reduce those dimensionalities? So we've been talking about multicollinearity, that there could be a correlation test that you can do. So when you are doing a correlation test, you would already know that there are some combination of variables that are correlated to each other. You should take a call whether which one to keep and which one not to keep. That will further reduce some of the variables in the data. Now, if you are not able to eliminate any of those, you can further combine them together to make a particular field. So let's say there is a example, to say with an example, there is a column that talks about spend and there is a column that talks about the revenue. So rather than keeping both of them, they might be spend or time consumed. And rather than keeping both the correlated variables together, you can create a ratio of time to spend in your data set, and that might be enough to reduce the dimensionality rather than keeping two variables. So always look for wherever you can combine certain variables together to make a new derived field, because that always indicates to a better interpretability of the model, and you can explain it in a better format as well. Not keeping unwanted variables in the data. Now, whenever you are when I'm talking about unwanted variables, if you'll see a traditional database, you will see fields like customer ID, timestamps, session ID, product IDs. These are the kind of fields that do not add any value to the data. There are corresponding values that have some kind of value or in a continuous or a categorical format that you can utilize this information. So it's always makes sense that you should drop these variables and use the variables that are actually referring to these particular keys. Now, again, similarly, the way we used statistics to compare whether two variables are associated to each other. Whenever you're solving a machine learning problem, there will always be a dependent variable. To check whether the independent variables, all the other variables in the data set are related to it or not, you can always check with an approach of t-test and chi-square. And if they are not coming significant, you can easily take a call on dropping these variables as well. Now, talking about some advanced ways of reducing data dimensionality, we will here speak about principal component analysis and factor analysis. Now, if we elaborate on these two particular topic, it will again be another session. But in nutshell, what I wanted to tell you guys is if you are taking a set of variables and they are equally important to you, you can't take a call of dropping those variables, and there is each variable is providing some set of information, but it is also enhancing the dimensionality or complexity of your data. You can obviously go through an approach of something called the principal component analysis, which is nothing but transform your variable into a set of 2 or 3 components, which explains the entire variability of your data. Here, the component 1 will explain, let's say, 60% of the variability of all the features that were there. Component 2 might further explain 20%. So even if you are able to explain 80 to 85 percent variability of all the columns that are in your data, you are fairly good in building a model. Whereas, and you will be able to train it much faster than if you had a set of 10 columns or a 20 columns in your data. Similarly, talking about factor analysis, it is again a similar approach. But here you do have some context of your variables in your data. So you know that there are some variable that caters to only demographics. So I can probably combine them to create one factor. Similarly, there are certain variables that are related to, let's say, transactions of a particular product or transaction on a website. And I can combine all those variables together to create one factor. So that factor is nothing but it represent a linear output of a linear equation of these three variables. So if you have, let's say, 4 or 5 transaction attributes in your data, you can combine them together and because using the factor analysis model, and it will give you a single output factor that kind of represents a linear output of those combinations. So these are data dimensionality approaches that you should be using when you are not able to solve dimensionality problem using the traditional approaches that we were talking in the previous slide. And if there's a huge chunk of data available and you can't go on dropping variable by variable, then I would highly recommend that you adopt techniques like PC and factor analysis, which will further help you in understanding how the data dimensionality is getting reduced. Moving forward, the last aspect that we are going to cover here is the data wrangling, or the major data wrangling approaches that we usually do in our day-to-day life. So I've categorized them into pivoting, which is basically spreading your data out long or gathering them into a concise form. It could be also aggregating into a form to make to create an output of an analysis come forward. So let's say I'm taking a small example of a store retail data, and in which you can see there is a date stamp, there's a fiscal week available, G of that particular, it's a categorical field available. You can also say this could be nominal. Now there is a source field that tells you whether it was an online purchase, it was a store purchase, or any other source. Now there is also a field for continuous fields, order, place, and revenue in this. So we do have a mix of all kind of variable attributes here. We can clearly see orders place as continuous fields, source as a categorical, geo as a nominal, and date timestamp also available. Now, when I'm saying I want to spread my data, it means for a particular field, I want to spread those categories as columns. It could be existing at categories at one place. It is similar to how we were doing one-hot encoding, but we are actually putting those real values in there. So if you've seen the spread example, what I've done here is the geo column in which it has unique values of Americas, Asia, Australia, Europe. I have spread that across the column. So that kind of exercise helps you in understanding what are the cuts, what is the different cuts that you can look at your data from. You might also want to transform into a long format in which you just want only one continuous field that could be used for any kind of exercise. Let's say you want to make it into a time series format in which you only have a date and a value field. So in that format, what you have to do is you have to create your two continuous field into a categorical format in which you are basically doing into a you are gathering your data. And what I've done is I've concise this order, place, and revenue column into a categorical field. And now we can clearly see there is a revenue field and order fields, where their corresponding values are still in the continuous format. Talking about aggregation, you can summarize your data at any level you want. There are SQL operations and Python operations available in which you can aggregate data at any level. And the aggregation techniques that you can apply on top of that could be related to summing those particular continuous field, taking a mean of those field, taking a standard deviation or min max. These are basic statistics that usually help us in doing most of the analysis. There are other customized function that people might kind of tend to use for their aggregation technique. So this is a gist of or data wrangling approaches that you might be using on day-to-day basis. And it's good to be familiar with these kind of approaches, because data structuring in a real world or real industry scope are kind of catering around these three aspects. Moving forward, and I think we are only having 5 minutes, and this is kind of the last touch point available in our current presentation. So I wanted to touch base on the data, day-to-day data that I have witnessed and I have worked on, and you might also, when you are starting your journey in data science, you might also witness using these data sets. So there could be a time series data, and an easy identifier of a time series data, there would be a date time field and there would be a continuous field. Now, this continuous field could be related to transaction, could be related to web traffic, could be related to anything. But considering it's a continuous field along with a date time field available, you can fairly consider it as a use case that you can use to build a forecasting technique. It could also be helping you in understanding what are the anomalies in this kind of data. Anomaly detection is a good use case that is currently being used. Now, in structure, survey data is another example that I would like to touch base on. This kind of data helps in can be used in clustering and segmentation approaches. Here you can see there is no dependent variable available. Basically, when I'm talking about dependent, what is something that you could help in generating or as a predictable output of it? These are basically using captured using surveys. People are rating each region based on what they feel on these particular aspects, and it can help you in understanding which, for a clustering use case, it can help you in understanding which set of countries are the most happiest. They would be clustered together when you use that unsupervised approach, and the most unhappiest would be also clustered in one kind of segment. So that is one of the use case, that whenever you see a data in which there is not a clear dependent output available, these are the kind of use case that you can obviously look into. Now, in terms of a kind of an example of a semi-structured data, I would say these are could be text review feedbacks that you might see on even for a movie. There are a lot of reviews there, or if you go on a Swiggy or a e-commerce platform, there are kind of reviews there for each kind of product available. So for these kind of textual data, you need to first do a lot of cleaning, but the kind of use cases that they solve is could be in sentiment analysis, could be in topic modeling. You could be using these kind of use cases. So there are a lot of use cases that you can always cater to from these kind of data sets. I've also taken an example of a pharmaceutical data which basically has a dependent variable. So this is one case where you can actually apply your classification techniques or regression techniques. Here we can see there are a lot of continuous variables available, although there could be categorical available, but we can further impute them into a binary class or anything that can help us in building a model. But whenever you see an outcome field that is basically wants you to, that hints you whether you want to predict a positive or a negative outcome, these are the use cases that directly hints you towards that. There could be a classification use case. It could be where you are using your naive-based SVM or logistic regression kind of model to further enhance or bring a predictable outcome. So in nutshell, these are like most commonly used data sets, and you can obviously further explore a lot of data sets that are freely available on Kaggle. Go through those case studies and try to apply the things that we have learned in terms of data cleaning, data understanding on top of that, and whether that helps you in building a particular model. So yeah, this was about the session, and I think we are about time. I'll quickly take few more questions that came in the last, and with that we will be for the ending the session.
Yeah, sure. Okay, we'll took some question answers from the attendees.
So there are questions on some, Nielsen has asked question on eigenvalues and eigenvector in reducing the dimensionality. So eigenvalues is basically the value that you generate out of. So for whenever you run a PC or a factor analysis, it it arranges your factor or components based on the eigenvalues of the factor that is there. So each variable, each raw variable contributes to creating a component, and eigenvalues is that associating score or associating vector value that you can end up in relating to the raw value. So let's say if a component was creating, and it is, if you have to associate with the raw variables, you will always look at what are the eigenvalues given to those raw columns, to the columns that ended up creating that component, and helps us in arranging. And that also tells you that component could be highly dependent on one of the variables that was used in creating that. So it is always good to understand how your component was created, but it is fairly a next step to PCA, that if you want to decode your PCA further, that would be one thing that you should look into as per from eigenvalue perspective. There is a question from Himanshu on handling imbalanced data. Yes, that is one aspect that was not covered here. Just to briefly talk about how to handle imbalanced data or category. So usually in imbalanced data might exist in categorical fields, that there are certain categories that are having high values. It could also be in a dependent attribute. So there are certain kind of sampling techniques that are available. What you basically do is, for the categorical field that has a low frequency count, you create duplicate or redundant rows of this and kind of add them, append them into the bottom of your data set. That is one of the traditional ways, but whereas a sophisticated approach of SMOT, which is random oversampling, is also available, that you can use to create. It basically creates duplicate values, but also alters the values of different columns to the some extent, so that it doesn't look a duplicate, but you are also arranging them in your data as to balance the categorical field. To choose in terms of different type of encoding. So I would honestly prefer you to go with one-hit encoding, as when you are creating, whenever there's a high set of categories available in a column, you would be encoding them from 1 to 50. Let's say if there are 50 categories available. Now that again will further require you to scale them between a certain range. So to avoid that, it is always good to create them into a binary fields, and it is easily interpretable also when you are building the model. Whenever you're doing a feature selection approach, when you are doing a variable importance check also on your model, these binary fields come out better in terms of the fields that are created as per label encoding. A good question on how do we understand whether to impute a mean or a median for handling null outliers. So whenever you have a normal distribution in your data, that means your mean and median are fairly close to each other. So in that case, you can adopt any technique, but it is a good practice to always take median imputation, that is the 50th percentile value, which will be equidistant from both the standard deviation. So you are not even putting that one value, you will not be deviating from the bell curve that gets created when you are checking the distribution. So it's a good practice. When you are not able to decide, take the 50th percentile value. I think, yeah, we are good with the outstanding questions we had, and we can end the session now, Saurabh.
Yeah. Thanks a lot, Varun. On behalf of Analytics Vidhya, I would like to thank you for your time and for delivering such a wonderful session. I'm sure our audience found it insightful, and hopefully we can conduct more such sessions with you in the future. Thanks a lot.